So thank you very much. This is Cosmic String Loop Collapse in full general relativity. I'm Thomas Helfer. This has been work done with Yosu Araquay and Eugene Lim. And so we use GR Jumbo. It's a numerical general relativity code with adaptive mesh refined. It's open source. And I think it's one code that you want to use if you do things that are typically not your classical binary black hole or your neutrons. So these are more if you want to do some more exotic stuff, this I think is the right code to use. So some of our collaborators who very kindly provided me these movies studied high dimensional black holes. We of course did some work with cosmic strings. There was some work done in inhomogeneous inflation. Of course, we still study black holes, and we recently also have studied black holes moving through a scalar field medium and experiencing dynamic friction. So one of the major selling point, of course, is the adaptive mesh, and this one without this project would not have been possible. Here you can see a ring loop. You can see very neatly how the adaptive mesh is following the cosmic string and make sure that it's always well resolved. So we are a small collaboration, which I feel very happy to be a part of, and it certainly it made me the scientist I am today. So I'm very grateful to be part of such an excellent group of people. And so what we simulated was, first of all, the Klein-Gordon equation. That's the minimum requirement for having a cosmic string. It made it a bit technically, for us more technically, more easier to also use the electromagnetic equation on top of it. And what our big innovation was in this work was, of course, Einstein gravity. So on the left side, you see actually a simulation where nothing seems to happen. That's exactly what should be. It's a static cosmic string which should not have any significant time evolution. Just sit there. This was a great moment for us because before that, our simulation was just continuously exploding, doing things because, of course, we just were trying to debug our code. And of course, at some point, this was working. So we were very ecstatic that it was finally working. So why we're doing this, of course, this is the area of gravitational waves, and cosmic strings are a source of gravitational waves. And we hope with this work to improve gravitational wave signals coming from cosmic strings, and thus facilitate their search. Also, these are very extreme events, so they give us they can give us some insight about the fundamentals of general relativity. So the specific scenario we looked at is we looked at a loop of cosmic strings. And if you set them up, they behave like rubber bands. So they will try to snap together. And they snap quite aggressively because at the end, they almost move at the speed of light. And if they reach radius 0, they unwind and disperse into radiation. If this one is heavy enough, you also can then form a black hole. And so the first regime is the first infall regime you can describe by Nambu-Goto quite well. This is very similar to describing black holes and point particles. However, you describe the strings as an infinitely thin line. So this works very, very well. The unwinding part you need to describe with a lattice field theory. However, for describing the black hole formation, you need full numerical relativity. And so we are very proud to be able to have achieved that. So just to give a bit of an overview of the parameter space. So for binary black holes, of course, you need at least 8 parameters. However, for our circular rings, we only need 3 parameters. And in the case where you do form black holes, we found that some of these parameters are less relevant for the resulting gravitational waves. So for example, the lambda parameter that determines the thickness of the cosmic string, but actually does not have any effect on the gravitational waves. And then for one that has an effect, but a trivial effect, is the radius r, which effectively scales linearly the mass of the string. And so if you increase this R by a factor of 2, you can then appropriately scale your gravitational wave signal and get the signal for that case. At least that's what we found with from what we saw from our simulation. Now, the only behavior where you have non-trivial behavior is the density G mu. And so this is because density G mu defines the velocity before you before you form the black hole of the cosmic string. So the Lorentz factor of this velocity is given by 1/4 pi G mu. So approximately, if you have a string which has a tension of G mu 10 to -6, the velocity of this, the gamma factor of this one would be 10 to the 6. So this would be move almost very, very, very close to the speed of light. It would be a very ultra relativistic event. We did a bit of a smaller G mu, so because of that, this was fast. What was fast technically possible. We simulated 4 times 10 to -3 G mu, and which is approximately a gamma factor of 20 before forming a black hole. So we did, of course, with Giachambo, as mentioned before. So this logo was done by Yosu. It's pretty impressive. Also, the visualization was done by Yosu, and lots of the simulation also, of course. And so here you can see the initial data. It's the energy density of volumetric run, and here you can see the mesh. So it's a very, very fine mesh. This was a very expensive simulation. It ran on hundreds of cores for several days. And now you can see below appearing the gravitational wave signal. Now the string starts to accelerate. It becomes fast, almost moving at the speed of light, where it then now forms a black hole. And you have the peak of the signal, and now you have this excited black hole that slowly rings down and a sense of the gravitational waves. So of course the big crowning achievement was for us to get the strain signal. So this was quite difficult, but this is very similar to binary black holes, where you have parts that are being described by weak gravity, so the in-spiral that you can describe very well by just 2-point particles, and then the merger part that you need to simulate with numerical relativity, and of course you can match these together. So we did something very similar. We had the merger part that we could calculate with Nambu-Goto and weak gravity, and the final part which we could describe with numerical relativity, and we merged them together. So one thing what was very surprising for us was the difference between the beginning strain and the final strain. And so this one is actually gravitational wave memory. So it's a permanent imprint of the gravitational wave passing through to the space-time. So this was a bit surprising for us, but in general, it's actually not that surprising, which we learned. So, for example, for binary black holes, you would also expect some memory. You typically don't see that in the signals that you often see, just because these come from numerical relativity, and getting the memory or reconstructing the memory is something quite difficult. So typically it's being filtered out and not being shown. So just to conclude very fast, now we are able to generate some really high energy collision that will give us some insight about the fundamentals of numerical relativity. Of course, this also gives us a gravitational wave signal, and this allows us to search for us. And hopefully, in the future, we hope to simulate more relevant events like cosmic string cusps that are more expected. And of course, we can also use that with the current luck. We can set some bounds on the event rate of this happening. And lastly, of course, the extension we hope to make is then looking at cusps of gravitational wave. But that's, of course, future work. One thing we did for fun is we looked at, we made a tiny video game where you can fly around in virtual reality around a collapsing field of cosmic string loops that then form here gray colored black holes and radiate off green gravitational waves I would have liked, if this would be an in-person conference, I could have shown you this in virtual reality. We could have flown around with Lisa. Unfortunately, because of the pandemic, that's the best I can do. So thank you very much for listening. I now will go over to some extra slides, providing some extra information to the things I just said. So feel free to stick around, or if you had or if you're enough. That was, of course, thank you for listening a lot. I'm going to wait a few seconds and then go on with the extra slides. All right, so it's going on with the extra slides. So I mentioned before, this here you see the gravitational wave signal over time. And here, this is not anymore the strain, but R psi 4, which is what we typically extract from numerical relativity. So here we ran with different lambdas. Lambda determines the thickness of the cosmic string. And you can see within our error bars, there's no significant difference between the different signals. So that made us to conclude that lambda has no effect or no significant effect on the gravitational wave signal. Furthermore, here the same with the scaling, and I just want to point out all of these psi 4 and the time here are scaled appropriately with the initial mass. So these are all normalized to mass 1. However, if you wouldn't do that, they would scale linearly. Of course, the amplitude at the time would then scale linearly with the different radii. However, that they are now the same, that shows that the linear by rescaling this linearly, and all the same, that shows that they show linear scaling behavior for the radius. Again, within our numerical accuracy. The numerical accuracy we try to represent here with the thickness of our lines. We try to make some estimates on our errors. Now, where we do not have any non-trivial behavior is in G mu. So here you can see many runs for different G mu's. Again, we scaled out the initial mass, and here you can see behavior beyond just linear scaling. And again, as mentioned before, this has to do with the initial velocity. By the way, you see like a bit more transparent part in the beginning. This is associated with initial data noise from that is not physical. This is just some artifact from how we construct our initial data, and it's quite common in numerical relativity simulation. So lastly, we also try to fit quasi-normal modes on the ringdown, and we did this for the L2 and the L4 mode for the two different runs. So, and for both of them, this is a nice consistency check. We got, within, of course, our numerical accuracy, very similar answers of the final mass of the black hole. This was a nice consistency check. Another consistency check that was pretty nice was the comparison with Nambu-Goto. So we try to track the position of the string as it falls in, and this here is in the plot. You can here see the y-axis, excuse me, the radius, and the x-axis the time. And we track the position of the star over time. And compared, we have that with Nambu-Goto, that's the black line. And indeed, they seem to overlap up until the point where the radius is more or less the string thickness. So really up almost extremely close to the point where you expect it to break down, it is consistent. So this was a really nice check. Just again, we wanted to make sure, since this was something completely new, that what we're doing is actually right. And well, a last and very interesting, nice thing we also find is we check the Hooke conjecture. The Hooke conjecture is a very simple conjecture where you just, which it's not a fully defined theorem actually, it's more like a rule of thumb. But this rule of thumb seems to work very well. So the claim is that if you can fit something within the Schwarzschild radius of the corresponding mass of what that thing has, it will form a black hole. So we try to estimate this one. And so you can see it here, this is the violet region is the expected is from Hubble conjecture expected region where you would expect to form black holes, and the yellow points are where we have dispersion, where we do not form black holes. And of course, the black points are the points where we form black holes for these specific parameters of the simulation. And so you can see it, this violet region is a very good predictor where you would expect to form black holes. But yes, all right. Lastly, I just want to show also we ran some dispersion case, and so this is of course in the Hubble conjecture diagram one of these points of the yellow points. And let me just jump slightly ahead. Where we start to see. So here you have multiple panels. Here this is again similar as before, a volumetric rendering of the energy density. Here what you can see is different slicing of the donut, of the bagel, depends where you come from. And here the first one here is the slice where you, I guess, when you want to apply butter or something, or this other one is the slice where you I don't know what you're going to do if you slice your donut like that. The tiny circle here is represent to the horizon of the cosmic string data. And lastly, also here we track the position of the star over time and compare it with Nambu-Goto again. And I play this. And what you can see, the string is again accelerating, or now moving at the speed of light now. Now it's very compressed. Does almost form a black hole. You can see it's almost completely fits into this region. However, it doesn't manage to bounces back and unwinds and produces massive amounts. It radiates everything off in radiation and gravitational waves in scalar field and electromagnetic radiation. Well, thank you for listening to all of the slides and to all of it. If you have any further questions, I'm very happy to if you just send them by email. My email is thomashelfer, just my name, everything together, @live, like live television.de. Thank you very much.